Hi, in this video we are going to see an example of the application of the convolution property of the Fourier transform. First, let us remember what we mean by the convolution property. If you have two signals, x1 with Fourier transform x1 of omega and the signal x2 of t with Fourier transform x2 of omega, then we know that the Fourier transform of the convolution of these two signals, x1 and x2, will have the Fourier transform, which is the product of the Fourier transforms. So the convolution operation in time domain is in fact a multiplication operation in frequency domain. Okay, now consider the signal x of t, which is the convolution of rect t with itself. That means we have the rectangular pulse signal, which is equal to 1 for t between -1/2 and 1/2 and 0 elsewhere. And x of t is the convolution of this rectangular pulse with itself. So first we remember the definition of the rectangular pulse, rect t. It is equal to 1 for t greater than 1/2 and less than 1/2, and 0 otherwise. Remember, in the calculation of the Fourier transform, if we have equalities or just strict inequalities, it will make no difference in the result. So if you wish, we can just put an equality as well. So rect t is the rectangular pulse, defined in this way. Okay, so how do we calculate the convolution of the rectangular pulse rect t with itself? So x of t is in fact the convolution integral from -infinity to +infinity rect of tau rect of t minus tau integrated with respect to tau. Okay. Now rect of tau is instead of t we have tau, so the definition is just the same definition. But what can we say about rect of t minus tau? First of all, we note that rect of minus tau is equal to rect of tau, because we have an even function as a function of the variable tau. And rect t minus tau is therefore rect of tau shifted by t. So for instance, I can plot here as a function of tau rect of t minus tau. So let t be, for example, such a positive value. So we are going to have the rectangular pulse shifted to t, or the 0 point is shifted to t. Therefore, this point here is t plus 1/2, and this point over there is t minus 1/2. Okay, now we have to calculate the convolution integral for all possible values of t. That means t from changing from minus infinity to plus infinity. Okay, for t less than minus 1, what can we say about the product of rect tau and rect t minus tau in the integral, appearing as the integrand of the convolution integral? So let us plot rect of tau and rect of t minus tau on the same plot. So this is tau. So this will be rect of tau minus 1/2 and 1/2, and the value is 1. Okay, I do not write anything on the vertical axis because I'm going to show both rect tau and rect t minus tau on the same plot. And for t less than minus 1, remember, in rect t minus tau, t is the midpoint. So we have this plot as the graph of rect of t minus tau. So this is t, this is t minus 1/2, and this point is t plus 1/2 and t minus 1/2. So from the graph we see that rect of tau and rect of t minus tau do not overlap. Their product is equal to 0. So rect tau and rect t minus tau is equal to 0. And therefore x of t is also equal to 0 for t less than minus 1. Okay, for t now greater than minus 1 and less than 0, we have the following graphical representation. So this is tau. Again, okay, let me draw a larger okay, this is minus 1/2 and 1/2. So this is rect of tau, and this point here is t. This point here is t minus 1/2, and this point is t plus 1/2, and this is t minus 1/2, and again the value is equal to 1. Okay, so in this case, rect of tau, okay, this one is rect of t minus tau. Rect tau and rect t minus tau overlap, and their integral, the integral of the product of rect tau, okay, from minus infinity to plus infinity, rect tau, rect t minus tau integrated with respect to tau is now non-zero, because the product of rect tau and rect t minus tau is non-zero, and the integral is, you see, the two functions overlap over the interval from minus 1 over 2 to t plus 1/2, okay, and therefore the convolution integral is the area of this rectangle, the shaded rectangle. So the area is, the magnitude is equal to 1, so 1 multiplied by t plus 1/2, okay, this point, minus 1 over 2. So the result is t plus 1. So for t between minus 1 and 0, the convolution integral turns out to be equal to t plus 1. Now let us see what happens when we choose t in the range from 0 to 1. Okay, so let us look at that next. Okay, so the third part of the calculation of the convolution integral will be for t greater than 0 and less than 1. Okay, again, let us plot the functions x of tau and x of t minus tau. So again, this function with magnitude 1 is, okay, this one is rect tau, and for any t, for instance, t here is a value between 0 and 1, so it will be okay, again, this function is now x of t minus tau. The midpoint is t, and this point here is t plus 1/2, and this point is t minus 1/2. Okay, in this case, they overlap over the interval from t minus 1/2 to 1/2. So we have this shaded area as the convolution integral value. So x of t, which is the convolution of x of, rect of tau, rect of t minus tau integrated with respect to tau will be equal to this area, which is again the value is here is equal to 1. So 1 multiplied by 1/2 this point minus t minus 1/2. Okay, so this will be equal to okay, 1/2 plus 1/2 makes 1. So we have 1 minus t. Okay. So for in the interval, t in the interval from 0 to 1, the convolution integral turns out to be equal to 1 minus t. And finally, for t greater than 1, okay, here, if we again plot x rect tau, so this is rect tau between minus 1/2 and 1/2. So this is rect tau, and for t greater than 1, rect of t minus tau will be given by means of this graph, or illustrated in the form of this graph. And as you see, they do not overlap. So in this case, rect tau and the product of rect tau and rect t minus tau is equal to 0, meaning that since they do not overlap, their integral, their product is 0, so the integral will also be equal to 0. Therefore, if we plot x of t as a function of t, and x of t is, remember, rect of t convolved with rect of t, it will be this triangular pulse. Which is non-zero between minus 1 and plus 1. For t between minus 1 and 0, the value of the convolution integral is t plus 1. So this is the graph of t plus 1. And for t between 0 and 1, we have 1 minus t. So this is the graph of 1 minus t. Therefore, we have this result. So the convolution of rect t with itself is equal to this triangular pulse. Now, what happens in the frequency domain? In the frequency domain, we know that the Fourier transform of rect t is sinc omega over 2 pi. So, by using the convolution property, the Fourier transform of x of t, which is rect of t convolved with itself, okay, will be equal to sinc omega over 2 pi square. Okay. Now, if we plot sinc omega over 2 pi squared, now remember that in the graph of sinc function, we have the main lobe, and then we have the side lobes taking positive and negative values. Now, since we take the square, for the Fourier transform of x of t, which is the Fourier transform of this triangular pulse, we will all have non-negative values for all omega. In other words, if we have this x of t, the triangular pulse in time domain, in Fourier domain, graphically, the Fourier transform of, we are going to show this as x of omega. The Fourier transform of x of t, in other words, x of omega, will have the main lobe, and then it will have the side lobes, but the side lobes will all be positive valued. Okay? And the side lobes will continue for both positive values of omega and negative values of omega. So, originally in the sinc function, we have side lobes taking positive and negative values, but because of the fact that in the Fourier transform of x of t, which is the signal obtained by the convolution of the rectangular pulse with itself, we all have positive values of the Fourier transform for all omega. Okay? So this is an important application of the convolution property. The triangular pulse, which is the rectangular, which is obtained by means of the convolution of the rectangular pulse with itself, is important in several applications. Therefore, this result is important in signal theory. Thanks for watching.